Well, welcome back. Today we're going to talk about round-off errors. We've seen these kind of show up several times in our code. But first, I'd like you to do the fast start activity, which you can find in Unit 1, Module 3, Lesson 3, round-off error. Do the fast start activity, and also download the startup file, which you won't be able to see until you do the fast start activity. So do that now. Pause the video. The other thing that is important to note is that we are approaching the Unit 1 exam. We will also have a quiz in this lesson. So after this lesson, we will have the Module 3 quiz. So we have two assessments. This is a major assessment, the unit exam. It will cover everything we've done inside this first unit, Modules 1, 2, and 3. There will also be some programming assignments that go along with this. So this is coming up. It's not going to be tomorrow, but it's coming up, and we'll have this quiz first. I just want to make sure that's well announced before we move forward. So when you look at the startup code, if I do double x equals 4.35, and I print out x plus a quotes, and then I do x times 100. First thing I have to talk about, the elephant in the room, is this is not in parentheses. So doesn't Java look at this as concat? Yes, it does. However, PEMDAS says the multiplication is done first anyway, so this calculation is actually done first before it does the concating. So we don't have to worry about putting this in parentheses. You can if you want to, but you don't have to. So what is the result when we do this? Well, you'll notice we get something weird. We get 4.35 when we print it out as a double, but as soon as we do a math calculation on it, we do some work on it, we get 434.9999994. So what is actually going on here? The issue comes in the way Java is trying to store the double 4.35 in binary. It stores it, it prints out 4.35, but really it can't store it exactly as a binary number. See, binary numbers aren't traditionally decimals. So Java does some math work in order to get it to be the value that you're interested in. So 4.34.999999994 mathematically is almost equivalent to 435. But then when you start doing integer operations on this thing, if I started casting this as an int, I would get 434, which is not what I want. And in fact, when we did that logarithm example I showed you at the end of the previous lesson, that's the reason why I had it add in the 0.0001, is to take care of that type of round-off error, which is not a great solution. It's actually a pretty lousy solution to have to add in some weird random decimal at the end of all of your answers when you cast them to ints to do the calculation. A more elegant solution is to deal with a number system that Java is actually really good at and doesn't have any issues with. So even if we do some other math calculations, like take 5 minus the value, we still get a weird result, 0.650004. 4.35 is actually stored as 4.3499999994. It's not 4.35. So the fix, here we go. The fix is to force Java to do integers, which it does absolutely perfectly. So we take x, which is 4.35, we set up a temporary value, and we multiply x by 100 and then cast it as an int. When we print that out, we get 434. So that's a problem. What we really want to do is round that number. So we don't end up with 434, we end up with 435. So we're going to take a new math function, which we haven't talked about yet, and we're going to take the 4.35 times 100 and then do traditional math rounding, which will be 435. And it might have some garbage after that, 435 point blah, 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 again, because of the way Java stores decimals. But we're going to cast that as an int, and when we're done, we get 435. So this math.round function and casting as an int to handle the conversion from this into 435 helps us solve the problem. But it's really an int now. It's not a double. But you might have learned in math that we can do decimals by treating them as fractions. So really, I can look at 4.35 as 435 divided by 100. I don't really need to treat it as a decimal. So if I wanted to do some math on this, I could take my number conversion and get 435, and then I can take 500 minus 435, rather than 5 minus 4.35. So again, I'm multiplying by 100. But then I'm going to multiply back by 0.01 to convert it back to a decimal. And Java very nicely just moves the decimal point over for me. It has no problem. There's no extra digits to deal with. So if I take 500 minus 435, I get 65. Multiply by 0.01, and Java very nicely moves the decimal point over for me, and I don't end up with any conversion issues. There's no extra garbage here. It's exactly 0.65. So what does this mean for you as a programmer? Well, it means that any time you do a calculation with a double, you need to be aware of the possible round-off error and account for it when you're testing your data. You see, it doesn't always happen. Some decimals, it's fine with storing that decimal as a binary value, and it doesn't end up with any weird extra junk. Sometimes it's not. So you really want to make sure you're testing enough data to make sure you've accounted for it. Or in your code, assume there's a round-off error and account for it right away, either by treating it as integers or by doing some type of add-on conversion, whatever you need to do in order to make sure you're dealing with that double appropriately. Yes, this is a pain in the neck, but it's part of Java. When Java sets up that memory location, it has stuff in there already. There's junk in there. It needs to fill up the entire space with your value. So anything after the initial decimal values is junk. Just like when you use your calculator and you do some multiplication or subtraction, you find out it gives you a whole bunch of decimal places. Sometimes you don't need all those. So we have to think about significant figures when we're doing Java, just like you do significant figures when you think about a course like chemistry. So yeah, this is going to come back. You can't just ignore this and let the computer handle it for you, because it's not going to handle it for you. It's going to end up with really poor results, and you could end up with a very, very wrong answer if you're doing several calculations. So there's a couple articles that talk about real-life disasters that were caused by numerical miscalculations. So this is a real thing. On February 25th, 1991, there was a Patriot missile battery in Iran that failed to intercept an incoming Iraqi Scud missile. The reason was because the calculation was done incorrectly. So the Patriot missile stored this number, introducing this error, which may not seem like a lot, but when you're talking about the speeds of missiles, it is a lot. So the Scud was outside the range gate that the Patriot tracked, and unfortunately it missed the value. But by going through this, the fact that the bad time calculation had been improved in some parts of the code, but not all. It meant that the inaccuracies did not end up canceling out when they kind of fixed the problem. So you got to be really careful as a programmer. There was an explosion of the R-Lane 5 air lane, June 4th, 1996. Again, there was a calculation error. The destroyed rocket and its cargo was at $500 million. There was a Euro page on the conversion of arithmetics. They had an arithmetic error, and they talked about these conversions. So when you're looking at the Euro conversion, there are these huge differences. That's real money that people are talking about when they're doing these conversions from one rate to another rate. So that's a pretty big error. So as you scroll through, you can kind of see some of these other errors. Feel free to read through these, and you can kind of see there's a whole bunch of them. Interesting to scan through. Then I have another article, and this is another one that talks about some of the errors that were caused, like this was the Vancouver Stock Exchange and some of the issues that were there, and they talk really specifically about the numbers and the actual calculation that had occurs causing the specifics about the Patriot system. So take a look, another article for you to look at, just to show you that these are real things. This is not just a little idea. This is a real problem that has to be paid attention to as a programmer. So these two articles will be here for you, linked at your leisure. You can read them. Once you're done going through those articles and taking a look at that, I want you to dive into the exit ticket and give that a shot. Once you've completed the exit ticket, go ahead and do this coding practice. So in this assignment, it takes a double, 1.473, and does a calculation, but this will produce a round-off error, so you need to write code to correct it. Assume no more than 3 decimal places will be used. Here's a sample run, and it should print out the correct result. Just as a quick review, scanner scan equals new scanner system.in is the code used to set up the scanner, and you need to use double x, scan equals next double to get a double, and int y equals scan.nextInt to get an int. Of course, in this case, we want to be getting a double, not an int. So you want to get the user to be able to put that in manually if you want to try some different test values instead of just typing in double x equals 1.473. So that's it for today. Work on that, and you'll submit your results here in the coding practice. And remember, we do have a quiz coming up after this lesson. So there'll be a quiz coming up that, again, you have to see me face-to-face for once you're ready for it. And then after that, we do have another programming assignment, which I'll talk about in the next video, and a unit test. So good luck. See you next time.